Hello students, it's Professor Tiffany again, or Professor Bridget, whatever you prefer. This week we're moving on to Chapter 2, and Chapter 2 kind of deals with the basics of what creates the hierarchy of organization, or the basics of what creates the foundation of living organisms, and that's atoms, elements, compounds, molecules, and so on. So remember last week when we were talking about the organization of living organisms where, let me see here, where atoms come together to make molecules. Molecules come together to make organelles, the little organs inside the cells. And then those organelles make up the cell itself. And remember, this is the smallest unit of life, the smallest thing we consider living. Cells come together to make tissues. Tissues come together to make organs. Organs come together to make organ systems. And then many organ systems come together to make the whole organism. And of course, we went farther than that. We learned about populations and ecosystems, etc. But my point is that we are going to start in our biology class building from the bottom up. So today is going to be concentrating on atoms and the bonds that they form to create molecules. We're going to talk also about the importance of water on our planet. And then gradually as we move through the semester, we'll learn about the organelles. We learn about cellular processes, like how cells process energy, how they reproduce, etc. And then at the very end of the course, we will get a chance to talk a little bit about tissues, organs, and organ systems once we get to the anatomy and physiology chapter. But chapter 2, what we're covering today, is essentially the chemistry of life. And you probably haven't had a chemistry class in quite a while, or maybe you have had a chemistry class, but you didn't like it, or you didn't, perhaps you weren't very interested, or maybe it's just been a really long time and you need a review. So one of the things I want to just let you guys know that this is going to be really basic. This is not going to be a complex chemistry lecture. We're just going over the very basics, okay? So let's move on, and let's define a few things first. I'll define for you what an element is. And an element is something that can't be broken down into any simpler substances. You can't break it or disassociate its component parts. It exists always as that individual unit. And elements are things like oxygen, nitrogen, carbon is a really important one that we're going to talk a lot about, and so on. And they're all assigned a symbol. And it's almost, well, I shouldn't say almost always, but oftentimes it's the first letter of the element itself, but not always. And the reason for that is these elements were named using the Greek and Latin words. So like sodium is an element, but its chemical symbol is Na. Well, that is short for natrium. That would be the Latin word for it. So, and when we look at the periodic table of elements here in a second, you'll see that some of the elements don't have symbols that are immediately obvious. So, oxygen, carbon, hydrogen, and nitrogen, they make up the majority of most organisms. Hydrogen is a major component, obviously, of living organisms. Carbon, all living organisms are carbon-based. Okay, so let's, we can move on from here. This table just shows you the abundance of elements in a human, on Earth, and in seawater. And so you can kind of see the ranking here. Hydrogen, oxygen, and carbon are the top 3 elements that make up your body. So if we look at the periodic table of elements, I'm sure you've seen this before, but it orders or organizes the elements in a very particular manner. You don't need to know how those elements are organized into the periodic table, but you should be able to understand how to read each square that you see in the periodic table of elements. So the example that they're showing you here is nitrogen. Its chemical symbol is N, and there are a couple of numbers here. The atomic number, right here in the upper left-hand corner, sometimes you might see it right here. Depends on how the table is put together and who put it together, but it's almost always on the top. So the atomic number is the number of protons, and we'll get to what those are. So that's the number of protons that nitrogen as an element possesses. And then the atomic weight, almost always down at the bottom, equals the number of protons plus the number of neutrons. You don't know what those are yet, and that's okay. We're going to get to that here in a second. So that's what those numbers mean. We can look over at sulfur, for instance, over here. So the atomic number is 16. So sulfur as an element has 16 protons. Its protons plus its number of neutrons is 32. And those are almost always, in all of these elements, almost always, with some exceptions, the number of protons and neutrons are equal. So if you divide 32 by 2, or if you split that in half, 50-50, then you've got sulfur containing 16 protons and 16 neutrons, which give it an atomic weight of 32. We can look at another example. Let's look at something strange that we haven't, well, I guess this isn't strange. Let's look at calcium, for instance. So calcium has 20 protons. That's its atomic number. And then it also has, so we already know it has 20 protons, right? So that means if its atomic number is 40, the other 20 subatomic particles that make up its atomic weight are neutrons. So 20 protons, 20 neutrons. And so there's a lot of information contained in this table. I mean, let's go back to here, our periodic table, and let's look at carbon on the periodic table right here. So one atom of carbon has 6 protons and 6 neutrons, because its atomic weight is 12. Protons and neutrons are almost always equal. Periodic table of elements. So that's that number that's here in the upper left-hand corner. So nitrogen has 7 protons. If an atom does not have 7 and it has, let's say, 8, for example, then it is no longer nitrogen. Look over here. I'll use a different color so you guys don't get lost. I use blue. If you look at the periodic table of elements, here's nitrogen right here. Let's say an atom, we know an atom has 8 protons. It's no longer nitrogen. An atom that has 8 protons now is a totally different element. It's oxygen. Or this atom over here, neon, has 10 protons. So that is something totally different than oxygen or nitrogen or any other element. And let's look at, where is calcium? Here it is, down here, right? So calcium has 20 protons. That's what makes it calcium, okay? We're not talking about the loss of calcium, but in this state, just calcium, when it has no charge, calcium is going to have, bad color, hold on. Calcium will have 20 protons, remember? That's what makes it calcium. And it will also have 20 electrons because it's uncharged. But if calcium loses an electron, say for instance, it loses something negative, so now it has 19 electrons. Now it has 1 more proton than it does electrons. So calcium becomes what we call an ion. It's charged, and that's usually indicated by a plus sign right next to it. So you might be saying, well, Bridget, you didn't tell us where in the periodic table are the number of electrons present. That's because they, in most periodic tables, they don't tell you. What's important is the number of protons and the number of neutrons. And on this periodic table of elements, you're just assuming that these are not charged particles. So that's why they don't tell you anything about electrons. So here, if we're assuming that manganese is it's not an ion, then we know it has 25 protons. Then we also know it has 25 electrons, because they're not showing you ions in this table. They're just showing you these elements when they're uncharged. So if we go to iridium, for example, the number of protons is 77. The number of electrons is also 77, because we're not showing ions in this table, we're just showing the elements. If we go to tin, for example, number of protons, 50. Number of electrons, 50. Each one of these elements represented on the table are neutral in charge, but some of these in nature have the ability to lose those electrons or gain electrons, and therefore then become what we call ions. Oh, and I drew all over this too. Okay, so here's chlorine in orange there. So chlorine normally has 17 protons and 17 electrons. But if it gains an electron, which it sometimes does in nature, it ends up having not 17 electrons, but 18. And so if there is one more electron than there are protons, the atom overall becomes negatively charged. Okay? That is quite useful. So we just were looking real quickly at the periodic table of elements. We know that an element is the smallest component of something that can't be broken down into smaller substances. And within elements, all elements are made up of atoms, right? So we could take, let's take carbon. Oops, that's a bad color. Let's take carbon, for example. Carbon is an element, right? Carbon can't be broken down into any smaller pieces. But carbon can exist as just one individual atom of carbon, or you might have, and this is more often the case, you have many carbons, thousands and thousands and thousands and thousands of carbon atoms all linked together. And each one of these carbons would be considered one atom of carbon, right? So this compound here, this molecule we just made, is still carbon, but each one of the carbon atoms is one discrete unit. So an atom is the smallest portion of an element that still retains its chemical properties. So one atom of carbon retains all of those properties that make it carbon. All carbon atoms will always have 6 protons. Well, I shouldn't say always. Almost always. And then it will also, its atomic weight should always be, it will have 6 protons, 6 neutrons, so its atomic weight will always be 12, right? And those particles, protons and neutrons, are often referred to as subatomic particles. So you'll hear me say that. Within an atom, there are different types of subatomic particles. One is a proton, another type we find is a neutron, and the third main type we find is an electron. So those are the 3 subatomic particles that we find in atoms. The protons and the neutrons are found in the center of the atom in a location called the nucleus. Protons are positively charged, meaning it's often written just as a plus sign. So think P, positive, right? So protons are positively charged. Neutrons, think like neutral. They do not have a charge at all. Okay, so these two particles, hold on. All right, sorry about that, you guys. My cat stepped on my keyboard and made my screen do all kinds of crazy things. So protons positively charged, neutrons are uncharged, and they exist in the center of an atom called the nucleus. And I'll show you a picture of this in a second. But remember, it's protons plus neutrons that make up the atomic weight. And then kind of orbiting around the nucleus are subatomic particles called electrons. And these are negatively charged. And really, when we talk about how atoms behave when they come in contact with other atoms, we're really talking about the electrons. So let's have a look to our periodic table. So what defines some atoms on our table? You go through it real quick. So this is just obviously just a really basic drawing, right? So we've got the protons right here, and the plus sign indicates that protons are positively charged. Then we've got neutrons here, and there isn't a sign there because they're neutral. They don't possess a charge. So you have protons and neutrons that make up the nucleus, and they're organized in the center. But then orbiting around, you see the negative sign. And this particular atom only has one electron, but you could have several electrons orbiting around that nucleus. It depends on which element it is. So let's go back to an table of elements. Let's do this more easily in your textbook, and if we can clarify that. Keep clarifying all these terms. I know that sometimes it's a little confusing, a little daunting, maybe even a little intimidating, but the more you work through it, the more you're able to understand and really be able to utilize this information. Okay. So what makes an atom of carbon an atom of carbon, or an atom of nitrogen an atom of nitrogen? The key number here, or the key thing that makes any atom what it is the number of protons. That should not change. So the number of atoms that an element has is called the atomic number. And we saw elements as a specific element, or an atom as a specific atom, is the number of protons. The number of protons we call the atomic number. If the atomic number changes, then the atom no longer is the same element. So I used carbon as an example, having 6 protons. So if carbon, or any atom, has, well, let's just say carbon has 6 protons. Its atomic number would be 6. Okay, oxygen has 8. That's what makes oxygen, the 8 protons. What makes carbon, the 6 protons. What makes hydrogen, hydrogen just has 1 proton. If that proton number changes, the element changes as well. Many times, atoms of elements have the same number of protons and neutrons. Many times, but not always. In some cases, atoms of the same element, they differ in the number of neutrons. And in this case, we call those isotopes. So let's take carbon, for example. We'll write it. There's the chemical symbol for carbon. It has 6 protons. And I'll just tell you, but if you were to look back at the periodic table, its atomic weight is 12. And that tells you that it has, again, 6 protons and 6 neutrons, because in most cases, the number of protons is the same as the number of neutrons, but in an isotope, it is not. So you could have an atom of carbon that has 6 protons. It has to have 6 protons because that's what makes it carbon, but the number of neutrons can vary. you might have 5 neutrons, for example. And so we would call that an isotope. There are some natural examples in nature. There's carbon-12, and there is carbon-14. So what does that mean? Well, carbon-12 is the standard. We have 6 protons, and then its atomic weight is 12. So that, again, that means 6 protons, 6 neutrons. So that's what we mean by carbon-12. But if you think about carbon-14, well, carbon-14 would have 2 extra neutrons. So here's carbon. We know because it's carbon, it has to have 6 protons. If it doesn't have 6 protons, then it's not carbon. So definitely has 6 protons. But in order to get up to 14 rather than 12, that carbon-14, that means it has 6 neutrons. So carbon-14 is an isotope of carbon. And that just means it has a different number of neutrons. At the periodic, like calcium does, sodium does, chlorine does, potassium does, they tend to gain and or lose. And look at chlorine. So confusing for you. Please don't. Okay, so we were just learning about the subatomic particles and their charges. Remember electrons? They have a negative charge. Protons have a positive charge. And neutrons, no charge. So they effectively are like just say 0, right? So an atom with equal numbers of protons and electrons, equal negative charge and positive charge means no net charge overall, okay? No charge to the atom itself. And a lot of atoms exist like this. But not all of them have equal numbers of protons and electrons. So in atoms that have gained or lost an electron, they're called ions. So electrons are negative. Remember, if you lose an electron, you lose something negative. And that means overall, you're positive. Think about it like this. You lose a negative influence in your life, or a negative something in your life. Your life becomes a bit more positive, right? So the atom then takes on a positive charge. Let me give you an example. Calcium, for instance. Let's look at electrons quite readily, depending on what other atoms are nearby. So we'll go back to our example of calcium. So when you see that positive charge there, you know that there are more protons than electrons. So calcium as an ion has a positive charge. If we look at chlorine, for example, that has a negative charge. So what's happened here to get that negative charge? We've gained an electron. You've gained something negative. So that's what that means. So chlorine, hesitate to reach out, and we can schedule an office hour. We can go over some more examples, and you can always ask as many questions as you like. So the way in which these atoms gain electrons or lose electrons is kind of like the atoms are either thieves, they have the ability to pull electrons away from nearby atoms, or they're victims. They can have their electrons taken from them. So an atom that is a thief, for instance, or really strongly attracts another atom's electrons, we say it has high electronegativity. Or the term electronegativity is a measure of how strongly one atom attracts electrons from another atom. And this depends on a couple of things that we'll get into here in just a second. But electronegativity really just means how strong is the pull from one atom trying to take electrons from another atom. Okay, so far we've gone over some key concepts about atoms and elements. I won't read this to you because we've just kind of gone over all of this, but I hope that you do read this and kind of summarize what we've learned thus far. And now we're going to focus on electrons and why they matter. We know that protons matter because the number of protons determines which element it is. We know that neutrons are negatively charged, and while they are important, we're not going to consider what neutrons do. So now what we're going to do is focus on those electrons, those subatomic particles that orbit around a nucleus. They're orbiting around the nucleus, kind of like a satellite orbits around Earth. It's the electrons that represent energy. And I'm going to keep mentioning this as long as we're here in the course, that it's electrons that represent energy, and energy kind of drives everything that we're going to learn about in the future. So those electrons are going to be that representation of energy and responsible for how atoms interact with one another. These electrons are going to be responsible for making bonds or creating connections between one element and another. So that's why electrons matter. Without electrons, you wouldn't be able to build large, complex molecules, and we wouldn't have life. So this is why these electrons are important. So there are a number of ways that you'll see different textbooks representing atoms and their electrons, and the orbitals in which we find the electrons. But the shell model is probably the most common, and what the shell model represents, and I'll show you in a sec, that, and this is kind of the rule, the law, that the first, you'll have, here's the nucleus of the atom with its protons and neutrons in the center, and then you'll have concentric circles around the nucleus. So you'll have that innermost circle or shell, then you'll have another one, and then you'll have another one. And it depends on how many electrons that particular atom has. That's what determines how many shells there are. And so you'll find those electrons orbiting in those shells. And I did this kind of backwards, but the first shell can only hold 2 electrons because that shell is too small. Each successive shell can hold up to 8. So you'll have 8, for instance, in this example, and then the next outer shell will also, or can hold up to 8. They don't always hold 8. Again, it depends. And I'll show you here in the next example. And it's these electrons in the outermost shell that are going to contain the most energy. Think of it like this. They're orbiting it around like a satellite orbits around the Earth. The ones in the outermost shell have the most energy. Think about being on a merry-go-round. And if you're closest to the center of the merry-go-round, you're not spinning very fast. You don't feel like you're spinning very fast. But if you move to the outside of the merry-go-round and sit or stand on the outside of the merry-go-round, you really feel like you're turning a lot faster, and you can feel the gravity pulling on you a lot faster. And that's kind of the way these electrons are. These electrons in the outermost shell are orbiting with the most energy. It's also these electrons in the outermost shell that are going to interact with electrons of other atoms. Okay, so let's have a look at the shell models here real quick, and what they look like for different atoms. And this is just a really basic representation of different atoms and their different shells. And this will also kind of be a review regarding atomic number as well. So let's look at sodium, which is the first one right here. So here would be the nucleus, right? And so that's where you're going to find the protons and the neutrons. And then it shows you each successive shell, and the yellow balls are the electrons. So as I said, the first shell can only hold 2 electrons because that fills up the shell. There's no more room for any more electrons because that's a pretty small shell. And then the next shell has 8. 1, 2, 3, 4, 5, 6, 7, and 8. And then the next shell only has 1 electron in that outermost shell. And the reason for that is sodium, remember, has 11 protons, or its atomic number is 11. So remember that atomic number means 11 protons. And sodium has, because it has 11 protons, it also has 11 electrons, right? So we had to make space for we had to figure out where we were going to put these electrons. So let's just go ahead and count all of them together, right? So we'll just start with the first shell, and that first shell has 1. Oops, didn't mean to do that. I'm sorry. Hold on. Okay, so the first shell has 1, 2, and then we've got 3, 4, 5, 6, 7, 8, 9, 10, and then the 11th one is here. Okay, so that's how we distribute those electrons. If you look at chlorine, chlorine has 17 protons and 17 electrons. So where do you put those electrons? You got to put them in the shells. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the last shell has 11, 12, 13, 14, 15, 16, and 17. So that's how those electrons are distributed. Now, those shells don't have to be full, like we saw over here with sodium. That outermost shell doesn't have to have 8 electrons in it. Just because it can hold 8 doesn't mean it does. So sodium only has 1 electron in its outermost shell, whereas chlorine has 1, 2, 3, 4, 5, 6, 7. So let me explain it again something to you. So chlorine has 7 electrons in its outermost shell, and sodium only has 1 electron in its outermost shell. Remember we were talking about electronegativity, and that's how electronegative something is, or how strongly an atom will pull or attract electrons from another atom. Electronegativity is dependent upon how many electrons are in the outermost shell. So you've got 7 total electrons in that outermost shell, but there's room for 1 more. So what chlorine really wants to do with all of those electrons and all of that negative energy, it's very electronegative. What it really wants to do, chlorine, is pull away an electron from some other atom. Because having 8 electrons in your outermost shell makes you stable. Chlorine, once it has that 8th electron in its outermost shell, is stable and what we would consider non-reactive. So chlorine is very electronegative because it has a lot of electrons in its outermost shell, whereas sodium only has 1. It only has 1 electron in its outermost shell. So sodium is sort of weak in that. It's very weakly electronegative. Sodium is very vulnerable. If it comes into contact with an atom like chlorine that's very electronegative, what's going to happen is chlorine is going to try and pull that outermost electron closer towards the chlorine atom than the sodium atom, kind of like stealing an electron. And that will satisfy that 8 electrons in chlorine's shell. This shell in sodium disappears because there's no electron to occupy it. And then sodium's happy too because it has 1, 2, 3, 4, 5, 6, 7, 8 electrons in its outermost shell. So sodium is happy. Sodium is stable. So this is one of the most common examples of these two atoms coming together to make a compound. Sodium, chloride. This is what we all know as table salt, right? So this is salt. This is how salt is made. So sodium can come together with chlorine. If we look at this example over here, argon's what we call a noble gas. It's very unreactive. It does not really react with anything else. Well, why? Because it's happy. It's got 8 electrons in its outermost shell. It doesn't have room for any more. It doesn't want to attract any electrons. These electrons aren't going to be easily pulled away. The argon is very electronegative, but it doesn't have any space to attract any more electrons. Let's look at carbon. Carbon is somewhere in the middle. Carbon in its outermost shell only has 4 electrons. So how many electrons would carbon like to have in that outermost shell? Carbon would really like to gain 4 more electrons to make that outermost shell have 8. So carbon is not super electronegative. It's not really vulnerable to having those electrons taken away. but it would really like to pair up with something else to be a little bit more stable. Oxygen is very electronegative. Check this out. It's got 6 electrons in its outermost shell. What it really wants to do is add 2 more to that outermost shell to make 8 to create a stable environment for oxygen. So a lot of times what happens with oxygen, here's the O for oxygen. O pairs up, or oxygen pairs up, one oxygen atom pairs up with another oxygen atom to become oxygen as a gas, as in the stuff that we breathe. So these are just some examples of the way in which we represent atoms and the placement of their electrons. And it's a way to visualize how those electrons are distributed, and a way to visualize which atoms might be very electronegative or susceptible to having their electrons removed as well. One last thing I think I didn't mention, but that outermost shell is always called the valence shell. So no matter how many shells or orbitals a atom has, the outermost one is always referred to as the valence shell. It's these electrons in the valence shell. Those are the ones that represent energy and represent the electrons that are going to interact with the electrons of other atoms. So when electrons of atoms come together, they create what's called a chemical bond. So it's this attractive force that unites atoms into a molecule. The attractive force is between an atom that is electronegative and an atom that has electrons that it's able to give up. So you have atoms coming together and being held together by this attractive force. When atoms are held together, it makes what we call a molecule. Molecules that are made up of 2 or more different elements are what we call compounds. So let me just show you some really simple bonds here, simple attractive forces. So carbon often comes to, let's do oxygen. So oxygen, like I mentioned earlier, oxygen atoms come together. They're bound together by that attractive force, and that unites atoms of oxygen into a molecule of oxygen. Often you'll see molecules of oxygen written like this. The same would be true for like nitrogen. An atom of nitrogen can come together with another atom of nitrogen to become what we call nitrogen gas. Let me show you an example of a compound. So compound is made up of 2 or more different elements. So I used this example before. Sodium is one atom, chlorine is another, and they come together to make a compound that we know as sodium chloride, or what we would commonly refer to as salt. Here's another one. Carbon coming together with 2 oxygen atoms. That's carbon dioxide. Carbon can come together with just 1 oxygen atom and be carbon monoxide. Nitrogen can come together with hydrogen to create ammonia. You might have potassium coming together with chlorine to make potassium chloride. Those are all different examples of compounds because they're made up of 2 or more different elements. So elemental oxygen and elemental carbon come together to make this compound. Elemental potassium and elemental chlorine come together to make potassium chloride. A mixture now is a substance that they will mingle together, but they don't bond. There's no interaction between the electrons of those atoms. So classic example would be like water and oil. Or, water and oil. Perfect example. Here are a couple of different ways that you might see these molecules represented in your book. So here's the what we call the electron distribution diagram. Don't worry too much about having to know that this is the electron, how it's represented in this electron distribution diagram. This is pretty much what we were just looking at, the shell model, right? But it's showing you how these two atoms of hydrogen are interacting to create hydrogen gas, which is H2. So you could see hydrogen gas written in its molecular formula. You can see it written this way, and it's how its electrons are distributed. You may see it written as its structural formula, where each one of the letters indicates the name of the atom, and then the line between them represents the connection between the two atoms. And remember, that connection or the bond between those atoms is created by that attractive force between electrons. We won't use this example often, but this shows you what's called the space filling model, and that just shows you the amount of space that's taken up by all of the orbitals or all of the shells that the electrons occupy. Like, this is like the physical space and distribution of those electrons. So you see oxygen, water, and methane, and you kind of see how those things are distributed. I often write or draw using the structural formula just because it's the easiest and least complex to draw, but also I'm a horrible artist. So it's here. This is just showing you that there are different ways to represent these molecules. One other thing I want to mention is something called a double bond. You may remember this from high school chemistry, or you may not. When you have an atom and two lines between it and another atom, like they have written here, that's called a double bond. Two lines is a double bond, one line is called a single bond. A double bond means that two electrons are being shared. So these two electrons from this oxygen are also being shared with these two electrons from that atom. So if I erase that, if I erase all that, then it's just like the lines, the lines are representing the sharing of energy here and the sharing of energy here. It's a double bond. Okay, so some of the information that you see on this slide is repeat. I was saying some of these things and using these terms on the previous slide, but remember that the outermost shell or the outermost orbital is referred to as the valence shell. And how an atom behaves or interacts is determined by the electrons in that outermost shell, in that valence shell. The more valence shell electrons that are present mean greater stability of the shell. So atoms really like to have those valence shells as full as possible. Remember, those valence shells can only hold 8 electrons. So really an atom would like to have that entire shell full with 8 electrons. The fewer electrons that are in that shell means that the atom gets less stable. Those valence shells, as you've seen, the electrons in those valence shells interact with other atoms to create chemical bonds. And the way in which they create chemical bonds is they can give up an electron. So an atom, let's say, that only has 1 electron in its valence shell is pretty weak. And it might just say, okay, here you go. Here, take my my valence shell electron, and it might donate it to another atom. An atom that is very electronegative, that maybe has like 7 electrons in its valence shell, when it's real electronegative, will pull away an electron so it can accept electrons from other atoms. And in some cases, like we saw with oxygen, those 2 electrons might be shared. So think of it kind of like tug of war, where you've got an atom on either side of the rope. The atom that is more electronegative is going to pull on that rope and win the tug of war. They're going to accept that electron from another. The weaker atom, so to speak, with only 1 or 2 or just a few electrons in its valence shell, they're not going to be very strong at tug of war, and they're going to say, all right, you know what, go ahead and take one of my electrons. But imagine two atoms that are equally electronegative. It would be like playing tug of war with 4 people on one side, 4 people on the other. It's a push. It's a tie, essentially. So what the atoms decide to do is, rather than struggle to pull electrons away from each other, they decide just, I say decide, obviously there isn't any consciousness, but what happens is they end up sharing the electrons or sharing that rope just to maintain stability. That's kind of the idea here, is atoms really like to be stable. So now that you know a little bit about how the electrons are distributed around an atom, and we know that electrons represent energy, and we know that atoms come together and create bonds, and they can share that energy, they can donate energy, or they can accept energy. But there's a law in physics called the first law of thermodynamics. Oops, can't spell. That should be an M. So thermodynamics. And that states that all energy in our universe is pre-existed from some time, the Big Bang. So in chemical reactions, or just in the universe in general, energy is never created. You can't make more energy. And energy is never destroyed. It's only transformed. So an example, let's see. Our sun. It shines down on our planet, and it delivers energy in the form of sunlight. And if our sun were to die out, for example, that source of energy would just kind of disappear, but it's not destroyed. The sunlight has been shining on the earth, and that energy gets transformed to, say, for instance, the plants on our earth. So let's say here's the sun. It shines down on our earth. It shines down on our plants, and this is going to be a horrible leaf. Yep. Shines down on our plants, on the leaves of our plants, and here's a plant leaf. And the leaves of those plants, they use that sun energy, but they can't use that sun energy directly. They transform it into another type of energy. And this is a process we're going to learn about later on. But when there's CO2 present, carbon dioxide present in the atmosphere, with that light, what they can do is they can make this high energy molecule called glucose. And a byproduct of that chemical reaction is oxygen. So it was plants that created a habitable planet for us by transforming sun energy into what we call chemical energy. So in this process, we're not creating new energy. The energy originally existed in the form of sunlight. And we're not destroying energy because we're making a new form of energy. We're making glucose. And so then we come in and we eat the plants, and then we use glucose as a source of energy for us, right? And in the kind of a byproduct of this whole process is oxygen, which of course we need to breathe. So we'll talk more about this when we get into energy. We don't need to know too much about this. But chemical reactions is what we're going to get into in the next lecture. And chemical reactions don't make something new, and they don't destroy something that was already present. They're only rearranging matter. They're only able to move atoms around to create different molecules. Let me give you an example. Here, I think there's an example on the next slide, so I'll try not to get ahead of myself. Hold on here. Okay, right below, I didn't even read the next sentence. The creation of water from hydrogen and oxygen is an example of a chemical reaction. So I'll show you the chemical reaction on the next slide, and I'll come back to what the reactants and are, but let me show you this. Okay, so in order to make water, which we know is made of hydrogen and oxygen, we have to have hydrogen and oxygen present in the first place. They're not interacting yet, The interaction comes during that chemical reaction, and that's what this arrow refers to. This is the reaction. This indicates that a reaction has occurred. So we start with hydrogen, we start with oxygen, and when this reaction occurs, what you get is hydrogen bonded to oxygen. So we're only rearranging things. We're not creating something new. It's not like, well, we started with hydrogen and oxygen and what we end up with is carbon and nitrogen. That would be creating new matter, a different type of matter. We didn't start with carbon and nitrogen, so we can't get a carbon and nitrogen product. We can only kind of rearrange these atoms to create something that's slightly different. So the atoms or molecules that we start with, those are referred to as reactants. A chemical reaction occurs, and the results are the products. Now, for those of you who have been in chemistry recently, this only will probably apply to you, or if you remember this, this first equation up here is unbalanced. So I included the balanced equation at the bottom. For those of you who don't or haven't had any experience with balanced equations, don't worry about it. But for those of you that were wondering what the balanced equation looks like, it's down here. Okay, I'm just using this as an example to show you essentially what a chemical reaction looks like. We are going to learn a whole lot more about chemical reactions as we move throughout the course. This is just your introduction, and I'm not going to rely too heavily on the chemistry here. So here's that same chemical reaction just in pictorial form using the ball and stick model, where you've got an atom of hydrogen here, an atom of hydrogen here, and they're held together by a single bond. So that means they're sharing an electron. Each one of them are sharing electrons. Same thing here, atom of hydrogen and an atom of hydrogen. So you've got two molecules of hydrogen. And then you've got an oxygen atom here and an oxygen atom here. And those oxygen atoms are held together by two sets of electrons, that double bond. And then what we get after the chemical reaction occurs are two separate molecules of water. Remember that energy is never created or destroyed, it's only transformed. It's shuffled to create something different. So if we just look at this in simplest terms, let's just look at it as red and gray balls. So on the reactant side, we've got 1, 2, 3, 4 gray balls. On the product side, we still only have 4 gray balls. So we haven't created anything new. We haven't destroyed anything. Everything that was present over on the reactant side is still present on the product side. It's just been rearranged. And the same is true with oxygen. On the reactant side, we started with 2 atoms of oxygen, and on the product side, we still have 2 atoms of oxygen. All we've done is kind of shuffle around. We've sent 1 oxygen atom to those 2 hydrogen atoms, and we've sent 1 oxygen atom to the other 2 hydrogen atoms. Just a reshuffling, a shuffling of the deck of cards, mixing things up to create something different, but not creating something new or destroying anything. Okay, so that's part 1 to this chemistry lecture. Stay tuned for part 2 and possibly a short part 3. Okay, email if you have any questions. I'm happy to help.